Okay, so in this video, we're actually going to be doing the proof for the fundamental theorem of calculus, your favorite of favorite things from Calc 1 and Calc 2. So, in particular, we're going to suppose that we have some f from the interval a to b to r as usual. We're assuming that this thing is differentiable and that f prime itself is also Riemann integrable. So there's an example in the book, or I might do some for another video, where it is definitely possible to have a function that is differentiable, but whose derivative, is not itself Riemann integrable, right? So it's possible that you could take a derivative and not then have an antiderivative, which seems unintuitive, but it's sort of one of the byproducts of how Riemann integration works. It's worth mentioning too that this motivates in future, for any of you going into the future sort of versions of analysis, this motivates why we might want to find different types or different ways of integrating. And in particular, getting around this problem is something that we can work on and sort of mostly solve this problem by doing a different type of integration called Lebesgue integration. None of that is something we'll get to in this class, but it is important to note, right, that this really is a required piece of the hypothesis, because if we didn't have that, we wouldn't know that this even makes sense, okay? But since we are assuming that, this definitely makes sense. We know that this thing has an integral. So really what the fundamental theorem of calculus, what this particular theorem is saying, isn't that this thing exists, because we're assuming that. It's saying that we have the actual value. So my goal here is to find out to find out what this equals, particularly to show that it equals that thing, okay? All right, so in the spirit of that, let's take P to be any cardinal partition. So fix or let P, which again we'll call some x naught, x1, up to xn, be some partition. And sort of partition, missed a letter. Sort of in particular, or sort of noteworthy here, is that I'm not declaring any features of P. I want this to hold for an arbitrary partition. So this is just some arbitrary partition, okay? So since we know that, since f of x is differentiable on AB, we can apply some, so for each I, so for, sorry, brain is letting go here. So for each I rectangle, right? Remember, these partition things are this order where the x0 to x1 is the first rectangle, and like x5 to x6 would be the sixth rectangle. So for each I with 1, not 0, less than or equal to I, less than or equal to n, by the mean value theorem, MVT, there is a CI in xi minus 1 to xi such that, so the mean value theorem says that I can take some part in this closed bounded interval, and I can get that the f of xi minus 1 minus the f of xi is equal to f prime of ci times the average, right? So this is the average slope. So this is going to be, so I should say this is the average slope. So I can do this as, say, xi minus xi. There we go. So in particular, excuse me, grab a thing here. So I didn't have to write it this way, but I'm hoping this will be clearer. So such that the average slope is the derivative slope at that point. That's what MVT says. which, moving this over, I can write this as f of xi minus 1 minus f of xi is this f prime at ci times xi minus 1 minus xi. Okay. Okay. So, why do I care? Well, so I'm going to make a couple observations. So first, notice I can do some tricky algebra that is nice. So if I were to have this sum, and why I care about this sum I'll explain later, but if I were to have this sum of f prime of ci times xi minus 1 minus xi, well, that is this. So this is just the sum, I equals 1 to n, of f of xi minus 1 minus f of xi, right? I suppose I did all these backwards. I mean, I didn't, because it's fine. It's just that that looks weird. Doesn't matter. So what is this? This is going to be, so this is a telescoping series, right? So this will keep cutting off the middle term. Eventually I'm going to have the very first term, x0 minus xn, which is a minus b, which is why I should have done xi minus 1, flipped those two and done it that way, so it would have been nice. So point is, I'm going to get the difference of the endpoints. So if I want to do absolute values or something, that would fix it, but I'm not going to worry about it right now. Okay, everything I wrote is correct. I'll adjust it in the next step. So I can do this sort of nice algebra. Whoop-de-doo, who cares? This thing seems to come out of nowhere. The other thing I'm going to point out is that f prime of ci is just some point in here, right? So in particular, I also have that if I were to take the smallest point, the mi, for that f prime of x, right? If I were to take the smallest point in that interval, it would be smaller or no bigger than the ci, right? So it would be no bigger than f prime of ci, which in turn is so this smaller thing is going to be less than or equal to that piece, but this is going to be less than or equal to the biggest value you could have gotten on f prime. Okay? So, in particular, if I were to do an upper sum, which are all these things, right? If I were to do some upper sum on this partition P on f prime of x minus the lower sum on, again, P on f prime of x, well, so, yeah, hold on, pause. I don't want to do minus yet. Let me explain it so I don't just jump ahead. So if I were to look at the upper sum here, right? The upper sum is the sum of capital Mi's, right? So this would be the sum Mi times the xi minus xi minus 1. Yeah, no, I was right. Want the leftmost one. Yeah, that's right. Brain is obviously shutting down. I need to take a break from all these videos. So that's this thing. But this capital M is bigger than f prime of c. So if I systematically replace it with something that is no bigger, I'm going to get that this thing is greater than or equal to this, right? I going 1 to n of f prime of ci times, if I write it the correct way this time, xi minus xi minus 1, right? Flipping those, which will flip those, and these. This is equal to b minus a, right? Sorry, this is f of, wow. Maybe I should redo this video. So let me fix this as I draw on my shirt. This is f of a, f of, woo. Yep, definitely time for a break. F of x naught minus f of xn, which equals f of a minus f of b. So in particular, if I do this bit up here, where I've switched it to get the right order, I'm going to get f of b minus f of a. I'll probably redo this video, but I'll probably keep this one up in the meantime, just because I'm trying to get through all of it, and I might re-upload this one, because I'm getting there. I just made a mistake or two along the way. All right, so importantly, the upper sum is bigger than that. Moreover, the lower sum, p to f prime, which is I going from 1 to n of little mi xi minus 1. This thing is going to be, because it's the smallest, right? It's going to be less than that, which equals that. So it's going to be less than f of b minus f of a. Okay? So in particular, what I actually am showing then is that the u of, so the upper sum for this particular partition on f prime, this thing is greater than or equal to f of b minus f of a, which in turn is greater than or equal to the lower sum for that same thing. But this is true for any partition, right? Because I made partition arbitrary, which means that I can limit this partition down to get that this actually tells me that the upper sum, a to b supremum, right, the inf of the upper sum, the best guess for f prime of x dx, that this thing is greater than or equal to f of b minus f of a, which is, again, in turn equal, greater than or equal to the lower best guess of f prime of x dx. And here's the last sort of important bit, which is that, remember, as I made a big deal about, we know that f prime exists. And if we know f prime exists, then we know that this upper sum and the lower sum are the same value. In particular, they are both just the Riemann sum, a to b of f prime of x dx for both of these. So that tells me that f of b minus f of a is somewhere between the integral and itself. So by the squeeze theorem, thus, this integral, a to b of f prime of x dx, is indeed equal to f of b minus f of a. Okay? And that's exactly what we wanted to show. Okay. So, aside from, I apologize, aside from flipping the order here and forgetting the F's over there, hopefully that didn't confuse too many people. Hopefully that's okay. This is the proof for the fundamental theorem of calculus, or the first fundamental theorem of calculus. All right, and that's it.